Okay, we are now on quiz number 5, the solutions for quiz number 5. Okay, we have a large skinny guy, mass of 2m, and a smaller guy with mass m holding a massless pole while standing on frictionless ice as shown. If the big guy pulls himself towards the little guy along the massless rod, where will they meet? Okay, so the center of mass of the system will not change. There are no external forces, so they'll meet at the center of mass. It doesn't matter that only the big guy is pulling. They still come together and they have to meet at the center of mass. Okay, let's find where the center of mass is. Center of mass is 2 times m. The position was -3. Okay, and then we have for m, the position was 3, so we plus m times 3, divided by the sum of the masses, which is 3 mass, 3 times m. So we get -3m over 3m, that's -1 m, so they meet at -1 m, -1 meter. Next problem, a generator's flywheel, which is a homogeneous cylinder, radius r, mass m, rotates about its longitudinal axis. The velocity of a point on the rim on the side is v. What is the kinetic energy of the flywheel? Okay, k rotational is 1/2 I omega squared. I is equal to 1/2 mr squared, so the k rotational is putting these together is 1/4 mr squared omega squared. So since v is equal to r omega, we have that we can replace this as v squared. We have 1/2 mv squared for the k rotation. Okay. Okay, and we have 3 forces are applied to a rod that rotates about its center. What is the net torque about this axis? Note that out of page is positive. Okay, so torque for force number 1, it goes in this way, so that's going clockwise, so that's into the page or negative. So it's negative force times the lever arm distance, which is r, the minus sign because it's clockwise. And then we have for T2, that's this force here. The force is 2F. The lever arm is r over 2. It's negative because it's going also clockwise. So we get negative Fr clockwise. Then T3 is this force here. The force is 2F. The lever arm is r, so we have 2Fr. It's going in this counterclockwise direction, that's positive. So if we add them together, negative Fr, plus 2 Frs, that's equal to 0. The net torque is equal to 0. Flywheel has a moment of inertia of 4 kilogram-meters squared. If a torque of 49 Newton meters is exerted on the flywheel to make it spin, what is the angular acceleration? Okay, the net torque is equal to I alpha. We're told that the net torque is 49, and I is equal to 4 times, so we have 4 times alpha, so alpha is 49 over 4, that's 12.25 radians per second squared. Okay, a light rod of length 2L has 2 heavy masses, each with mass m, attached at the end and in the middle. The axis of rotation is at one end as shown. Okay, so we can neglect the mass of the rod. It's a light rod. If the bar is released from mass, what is the magnitude of the initial angular acceleration? So first we get the torque due to this force here. We'll call it number 1. The force is mg. The lever arm distance is L. It's going clockwise, so we get the negative sign, mgl with the negative sign. For number 2, we have this force, which is also mg. The lever arm distance is 2L, so it's minus mg2L. It's also going clockwise. Now, so we have the net torque is minus mgl minus 2 mgl, so that's negative 3 mgl. Then torque net is equal to I times alpha. So alpha is equal to torque net divided by I, so it's negative 3 mgl divided by the moment of inertia. Okay, what is the moment of inertia? We have to do a little calculation on the side here. We have the moment of inertia due to this guy. It's at a distance of L, so ml squared. Okay, that radius is, if you want to call it the radius, r. So this radius is L. And the radius for the second mass here is 2L, so m2L quantity squared. So we get 5 ml squared. So that's what goes in here for the moment of inertia, 5 ml squared. So we get negative 3g over 5L. Next problem. A mobile is constructed from the metal bar and two wooden blocks as shown in the figure. Okay, the metal bar has a mass of 1.0 kilograms and it's 10 centimeters long. The metal bar has a 3 kilogram wooden block hanging from the left end and the string tied to it at a distance 3.0 centimeters from the left end. What mass should the wooden block hanging from the right end of the bar have to keep the bar level? Okay, so we have 3 kilograms here, unknown mass here. We have 3 kilograms times 9.8, and this is the rotation axis. So we can calculate this distance we're told this is 3 centimeters. Okay. So now this distance to the center of the rod. So the weight of the rod should be placed here at the center of mass. It's 1 kilogram times 9.8, and then we have this distance will be 5 centimeters. It's half the length of the rod. This will be 2 centimeters. Now this will be another 5 centimeters as well. So this is the force m times 9.8 meters per second squared. So we can go and calculate the torques. Net torque must be equal to 0. Torque of number 1 is here. It's going counterclockwise. So it's going counterclockwise, so it's positive. The lever arm distance is going to be 3. It's going to be 3. So we have 3 times 9.8 times the distance. I mislabeled here. The torque for force for this number 1 is 3 times 9.8, so 3 times 9.8 times the lever arm distance, that's 0.03 in meters. That's positive because it's counterclockwise. And then we have, for number 2, it's going clockwise. So it's the negative sign. The mass is 1. So 1 times 9.8 times the lever arm distance, which is 0.02. And for mass 3 here, it's going clockwise. So it's negative, and the mass is m times 9.8 times lever arm distance is going to be 5 plus 2 centimeters, so 0.07 meters. So the net torque is going to be sum of all these together. Okay, the 9.8s are everywhere, so we can divide by 9.8. And we get that m is equal to 1 kilogram. Okay, number 7, a solid sphere of uniform density, weight 3.6 pounds, starts from rest and rolls down a ramp. H is equal to 1.59 meters. Theta is equal to 22.7 degrees. Find the speed of the sphere's center of mass when it reaches the bottom of the ramp. Okay, the mass will cancel out, so this crazy units of weight and getting the mass, we don't have to do that here. So it's rolling without slipping. So we have equation V is equal to omega r. The moment of inertia is 2/5 mr squared. So the total kinetic energy is the translational kinetic energy plus the rotational kinetic energy. So we have 1/2 mv squared. It's 1/2 I omega squared. But I is 2/5 mr squared. And now omega. So then we have 1/2 and 2/5 mr squared omega squared. But V is omega times r. So that's this part here is v squared. Okay, so we have 1/2 mv squared, and then we have 1/5 mv squared. So 1/2 plus 1/5, that ends up being 7/10 mv squared. Now we can use conservation of energy with this total kinetic energy. So the initial kinetic energy is 0. The initial potential energy is mgh, and k final is 7/10 mv final squared. The final potential energy is 0. So now we have these guys are equal, so we can solve for v squared is equal to mgh divided by 7/10 m. The m's cancel, and we get 9.8 times 1.59, the height given, divided by 7/10, and we get 22.26. Take the square root, we get 4.718. Number 8, a car drives west. In which direction do the angular velocity vectors of the wheels point? So if the car is going in this west direction like this, okay, then the wheels are turning like this. Stick your thumb in the direction, spin around so your fingers are going in the direction of the wheels, and your thumb is going in the south direction. Okay, going like this, and my thumb's going in the south direction. So that was the spin around right hand rule. Now, they want to know the x component of the torque for a force that's 25 in the in the direction and 9.4 in the y direction, 0 in the z direction, and a particle is that r is 1.8 in the x direction, 3.5 in the y direction. Okay, so the torque is equal to r cross f. The components of r is 1.8, 3.5, and 0. The components of f is 25, 9.4, and 0. So we write down the components of r and then the components of f. We want the z component, so we strike out the z component here. We cross multiply to get the diagonals, 1.8 times 9.4, minus the product of the off diagonals, 3.5 times 25, and we get negative 70.6 Newton meters. Now we have a toy car. It's moving, it has a mass small m. It's placed on a disk of mass capital M. Okay. Everything's initially at rest. And so now the disk has a small groove to keep the car moving on the circle. When the car is switched on, it accelerates to angular velocity of omega c. What is the angular velocity magnitude sine of omega d of the disk when the car has reached the speed? Okay, so this is conservation of angular momentum. There's no experimental torque in the system. L final is equal to L initial, which originally was 0. Okay, so L final is equal to I times omega for D plus I times omega for C. And the sum must be equal to 0. So omega D must be minus IC omega C, this guy here, brought to the other side, divided by ID. So IC is mr squared, we're talking about for the car. So the car is a point particle. It's at a distance r, so it's small mr squared times omega c. For the moment of inertia of the disk is 1/2 capital M r squared. And we can get rid of the r squareds, and we get minus 2 because the denominator becomes the numerator. We get negative 2 small m over capital M omega c.